Hello folks, Rashid here. Thank you so much for joining, and we are looking into 12-step interrupt action, and we already looked into 5 steps in the previous video. So if you have not watched previous video, please watch that. That is really important for you to understand this video. Okay, and before I start on those next steps, what I wanted to tell you was where the next step. Okay, the steps start from 6. That this simple picture that I am teaching you. Okay, I taught you the CPU internals, and now I'm teaching you some CPU internals along with the peripherals, right? So we are learning a simple SoC architecture. And this architecture, right now architecture, then comes microarchitecture, then comes implementation, then comes verification, then comes physical design. So using this very simple example, okay, we are building a chip. So the commercial chips that you see, or the companies where you're gonna work later on, it's the same thing. It's just on a bigger level and more complex, lot more features, okay, lot more cores, lot more peripherals and all that. But the core of it, the fundamentals are similar. Okay, so now for you learning all this, learning different stages of chip design implementation is very important. And later on, when you are working on, a big physical design of a big block, RTL implementation or validation of big block, then at least the rest of the picture is clear to you, right? You're not lost, okay, where I am, what is on my left, right. The bigger picture is clear to you. And even if you have to go to architecture, or you have to go to physical design or different areas, right, things are clear to you. And you can even spend time in the companies where you go. There is always an architecture document. There always a microarchitecture document, and you can read those. And these simple things will give you a good background, so that when you read those detailed, complex, lengthy documents, then you can at least understand, okay, where we are going from. So interrupt. Okay, we learned CPU architecture, right, internal, but CPU on its own, nothing. It has to communicate with the rest of the world. And the rest of the world comes through some sort of IOs, inputs and outputs. And there are components, controllers on those. And there is an interrupt controller. So what I'm giving you here an example, okay, when you have your chip there, and externally, let's say, is an industrial environment, and an input comes, it's a thermal sensor. When the temperature is more than a certain level, you need to turn on a fan on the output. Very simple case, right? Now, question is, what kind of hardware components come in the way? What is that fundamental process that happens? And we're not going into all the details of it. We don't need that right now. Later on, when we implement, or we take an implemented version from somewhere open source, then we will look into it and how it is being implemented, and that's where we look into every detail of it. But right now, we're just trying to see, okay, what is the flow of it? Okay, so that I thought it was important to give you that background, so that it gives you the right perspective of why you need to understand this one. We're not just looking at it just for the sake of it, right? There is a reason for that. Every course that I build here, there is a reason for it. It's not a college or university course where I'm completing some credits there. So I have sketched this entire curriculum for you, and there are things that I need to finish. But this one right now, it's important for you that you know the architecture of it. Anyway, so the last time until 5 steps, what we did was, when interrupt comes, already there's control and status register we talked about last time. Okay, so you should know those. So now we call interrupt service routine. That interrupt came, okay, communicated through interrupt controller to CPU. Now we need to serve that. Okay, we need to do something with it. And that piece of software is called interrupt service routine, and it is there in our Flash. We can write it later on into our SRAM, but right now it's still, in our case, it's sitting in Flash. So what it does is, as I said, okay, CPU was already doing something. right? It was executing an instruction and was already in a flow of that. So we need to stop that flow. And if you remember, when it's working on an instruction, it might be using some of the temporary registers, T0, S0, and all those. So now we need to serve the interrupt, but all those registers we need to save somewhere. So this context mean now those temporary registers we need to save somewhere, right? We need to find out who interrupted. Okay, so we need to go and get that information from interrupt controller. Okay, interrupt controller provides that ID number, and then we know that okay, it is that particular GPIO 0 that we need to talk to. All right, so then our this service routine, this software works with eventually a CPU that is executing these instructions, right? So the instruction of this software or interrupt service routine, CPU executes that, and it knows that okay, which GPIO it needs to talk to. So then it talks to that GPIO through that controller. Now how? So CPU and GPIO controller are connected through a system bus. Okay, and that GPIO controller has a particular address, and within a GPIO controller, each GPIO has a certain register which tells us the status of that GPIO or what else we need to do there. So all you need to do is, all CPU needs to do is, in this case, generate right address so that system bus, the decoder of address, there understand that this data that CPU wants or sending or want to receive, this is for that particular GPIO within GPIO controller, right? That is called memory mapped thing. All right, so now it understands. So once it know that it is that GPIO, okay, what does a service do? That interrupt service, what is that service? The service is okay, because interrupts came, that means we need to turn on fan. So our interrupt service routine, what it does is it knows that it needs to turn on the fan, and the fan it already knows is on GPIO2. Those initialization we do in the beginning. Okay, so then it sends the address on the system bus. The decoder of the system bus understand that this is for GPIO controller, and within GPIO controller understand for GPIO2. So it sends the one signal, maybe 1 or 0, whatever that signal, so it sends it, and the fan externally is turned on. Okay, so now our interrupt service routine, ISR, needs to tell that okay, I'm done, guys. The service routine has finished its job, so there must be a register telling that its job is done. All right, now what we need to do is, when its job is done, now what we need to do is we need to go back. We need to put CPU exactly in the state where it was before that interrupt came, right? Right before the interruption, whatever the state of CPU, we need to get that. And when I say state, mean the state of the registers, because all the operation within RISC-V are happening on the register. Data is brought from with special instruction from the memory into the register, and then all the actions happening, all the operations are happening on the registers. Okay, so we need to pull those registers back from the scratch space, right? M-scratch register, which was pointing where the scratch area is. Then whatever the PC state is, because we updated PC with the new address of the service routine, now we need to update the value of PC with the address that it was supposed to be with whatever the previous continuous flow of instructions was happening, right? So we do that, and now we just, because when we were serving that interrupts, we kind of disable that. If new interrupts come for something else, in our case, we are building a very simple system. We don't have too much priority. Maybe later on we will say, okay, we have some priorities, but in this case, whenever we're serving one interrupt, we say, okay, we cannot serve another interrupt, hold on, do something, or maybe ignore it, we'll see. But right now I say, okay, now all the interrupts taking is enabled, and now CPU is ready to start that code that it was doing before interrupts. All right, folks, that's it, right? So this picture, it just says, okay, this picture was Yeah, this picture was through GPIO and all that we looked last time, and this one is okay. It sends signal to interrupt controller, it sends signal to the GPI controller to turn this signal on, and this IO acts as an output and it's connected to fan. So that is simple, right? Okay, hope you got that, and we will see each other in the next video in another topic. We don't have that many videos left on this peripherals or RISC-V, so RISC-V topic is going to finish pretty soon, and then we will start into system Verilog or microarchitecture. All right, thank you so much for watching. See you next time. Bye.